Welcome to class number 21 of transport phenomena in mesoscopic and nanoscopic systems. So last day we were discussing a system with one contact, and we saw that the expression for the current in this case is precisely given by this expression. So if we have a two contact system, then we have two source terms which are S1 and S2. So let me just write it here. So we have two source terms. However, we will not be dealing with these two source terms at once. The only way the source terms would enter, both these source terms would enter into the equation for current is through the wave function psi. Okay. Otherwise, let us consider the left contact. So at the left contact, or which is also contact number 1. So let me draw this approximate figure over here. We have this contact 1 and we have this channel over here, and then we have this contact 2, and these two are coupled via this matrix tau 1, and these two are coupled via this matrix tau 2. Okay, and S1 again is precisely, as you know, it is tau 1 phi 1. S2 is precisely tau 2 phi 2. And if we write the expression of current at the left contact, it is the current entering into the channel and entering into the channel from contact 1 and also exiting from the channel into contact 1. So if we write these two expressions, this net current is I, which is equal to I in minus I out. So this is I in, and in the opposite direction is basically I out. So there is no space, so let's skip that writing part here, but I'll just write directly over here. So this is from our earlier expression, this is basically equal to psi dagger tau 1 phi 1 minus phi 1 dagger tau 1 dagger psi divided by IH bar. So this is basically I in, which is also the inflow, and minus x1 dagger tau 1 dagger psi minus psi dagger tau 1 x1 divided by IH part, which is basically the outflow. Okay, so this is basically this part is basically I in, and this part is basically I out. Okay, now note that in this expression there is only this term tau 1 phi 1 here. Why? Because we are considering the current that is entering from contact 1 into the channel. Similarly, in this expression over here we have this x1 tau 1. Again, the same reason that we are basically considering the current that is getting out from the channel into contact 1. Okay, if we would consider this right contact over here, that is this interface, in that case this tau 1 phi 1 would be basically replaced by tau 2 phi 2, and this x1 tau 1 would basically be replaced by x2 tau 2. Okay, now we have to basically put the values of psi, because we don't want to keep this expression in terms of psi, and as we know that psi is equal to gs, where g is the Green's function of the channel and s is the source term. S is basically equal to s1 plus s2, so this is equal to g times s1 plus s2. So remember that in these are basically functions g, s1 and s2, and in, I would not say exactly functions, but these are mainly operators. mainly this G is basically an operator over here. Okay, S1 and S2 are not operators. But here, since we are considering the numerical aspect or the computational aspect, G is basically a matrix. Okay. So now let us simplify this term over here, and we will simplify in a way that we did earlier. So that's not much difficult. So let me consider this term over here. So phi dagger tau 1 phi 1. Now tau 1 phi 1 is basically equal to S1. So this is equal to S dagger G dagger, and this is S1. Okay, now this is basically, note that this part is basically a number. Okay, this is basically a number because this is a row matrix and this is a column matrix, so this is basically a number. Now this number, this is also the same number, so this number is equal to the trace of this number, because trace of a number is equal to that number itself. So this is also equal to trace of S dagger G dagger S1, and this is equal to trace of, by the property of cyclic order, this is equal to S1 S dagger G dagger, which is equal to trace of S1 S1 dagger G dagger plus S1 S2 dagger G dagger. Now note that S1 and S2 are the source terms, which are equal to tau 1 phi 1 and tau 2 phi 2, and since this phi 1 and phi 2 are not related, that is they belong to the contact, so these are not correlated wave function actually. Okay, so if I take the average correlation of the wave functions in contact 1 and the wave functions in contact 2, then it would come out to be 0 because their phases are not related and they are randomized with respect to each other. So basically what we have here is phi 1 dagger phi 2 equals to phi 2 dagger phi 1, this is equal to 0. Okay, so when this is 0, this term is also equal to 0. Okay, so we basically get trace S1 S1 dagger G dagger. Okay, so this is S1 dagger G dagger. So now this entire term over here, this let me write in a second page. So this basically becomes I in equals to trace of phi 1 dagger tau 1 phi 1 minus phi 1 dagger tau 1 dagger psi divided by IH, and then I make replacements. I replace this by S1 and S1 dagger respectively, and I replace this psi 1 by GS, and I put the correlation terms to be 0. So this basically becomes equal to trace of 1 by IH bar S1 S1 dagger S1 dagger G dagger minus G. Okay, now I basically write this I as minus I, so 1 by H bar trace of S1 dagger, then I G minus G dagger, and this is precisely equal to the spectral function, so I would write it as 1 by H bar trace of S1 dagger A. Okay, now this S1 dagger, this is equal to tau 1 phi 1 dagger tau 1 dagger. So we replace this phi 1 dagger by the spectral function, and we write it as integral of dE by 2 pi tau 1 phi 1 dagger we replace it by integral dE by 2 pi a1 f1 tau 1 dagger, and then we basically replace this entire part. What is this part? This entire part is the broadening matrix due to contact 1. We write it as dE by 2 pi, the broadening matrix due to contact 1, which is gamma 1 and f1. And f1 actually is a function of energy. This is the Fermi function. So I mean this A matrix is also basically a function of energy. So everything is a function of energy here. So I'm not writing the argument. Okay. So inflow in that case, what is in the inflow? I in. This is basically from our previous expression. We just noted that this is 1 by h bar trace of s1 dagger A. So 1 by h bar trace of s1 dagger A. So this basically becomes 1 by h bar integral of dE divided by 2 pi f1 trace. f1 is basically a number that depends on energy. So trace of gamma 1 A. So put third brackets here. Okay, so this is basically the inflow. So in a similar way, we have already done the calculations previously, so I am not redoing it. In the case of two contacts, you can easily figure it out. So if you repeat the same calculation, you can get this outflow as 1 by h bar integral of dE divided by 2 pi and then trace of gamma 1 Gn. Okay, so we define this variable IE, which is basically a function of energy, as trace of gamma 1 A f1 minus trace of gamma 1 Gn, and the total current I or the net current I can basically be written as, so this is the electronic current actually, 1 by h bar integral of dE divided by 2 pi and then IE. Okay, now if you want to calculate the conventional current, how the conventional current is measured, it is basically the charge per unit area. This is the electronic current, which basically measures the number of electrons flowing out per unit time. So if you want to calculate the number of charges flowing out per unit time, you have to multiply it by Q. So I will write it as I conventional, where IE is basically given by this expression here. Okay, now we'll move on to Landauer's formalism, and that is where we would like to end this section. Now here note that this expression IE, this is related to the current that is flowing at an energy E, and this expression here has to be integrated over energy to get the total current. Okay, so this is related to the current at energy E. Now let us see if we can simplify and make this equation more compact. So this IE is equal to trace of gamma 1 A f1, and then we can actually put these two factors in these two matrices in trace together. So we just put them together, gamma 1 Gn. Now let us look at this, what this expression basically is. So gamma 1 A f1 minus gamma 1 Gn, this is equal to uh, gamma 1, and then A is basically equal to A1 plus A2, where A1 is the density of states inside the channel that is contributed by contact 1, and A2 is the density of states inside the channel that is contributed by contact 2. Okay, so F1 minus gamma 1, and Gn is basically A1 F1 plus A2 F2. So A1 F1, let me write it in a separate line, minus gamma 1 A1 F1 plus A2 F2. Okay, so now two terms cancel here, that is this gamma 1 A1 and F1, this basically cancels with this gamma 1 A1 F1. So we are left with two other terms which are basically gamma 1 A2 F1. So gamma 1 A2 F1 minus gamma 1 A2 F2 F2, which is equal to gamma 1 A2 F1 minus F2. Okay, now this is the current at energy E, or this is proportional to the current at energy E that enters into the left contact, or contact that enters into the channel from the left contact, or contact number 1. So write it here as I1E. This is the net current that enters from left contact. Now if we would do the calculations for the right contact, or contact 2, we would get the net current as I2E is equals to, so we interchange 1 and 2 here because now we are going to contact 2. So this would be gamma 2 A1 and then F2 minus F1. Okay, so when we discuss the total current, or when we talk about the total current, so this basically becomes I is equal to, so if we consider the charge current, this is equal to Q by H bar integral of dE divided by 2 pi. So we have a trace here actually, which I forgot to write, so this should be the trace of this matrix, and this one is also the trace. Trace of this matrix, trace of gamma 2 A1 F2 minus F1. F2 minus F1 we can keep outside the trace, okay, because F2 minus F1 is basically a number. Now this must be equal to minus Q by H, the current that enters from contact 2, because if current is entering from contact 1, then the current should exit from contact 2. Okay, so this expression here is basically of the net current that enters from contact 1 or contact 2. So if current is entering into contact 1, it is given by this expression. So in that case current is exiting through contact 2, so it should be minus of the entering current actually. So minus Q by H dE divided by 2 pi trace of gamma, sorry, this is gamma 1 A2 actually, so gamma 1 A2, and this is gamma 2 A1, this is F1 minus F2, and this is F2 minus F1. Okay, so this means that if the current that enters into the channel from the left contact is equal to the current that exits the right contact from the channel, then this trace of gamma 1 A2 must be equal to trace of gamma 2 A1, and this is indeed the case. Let us see how. So this trace of gamma 1E, so trace of gamma 1E, this is basically equal to trace of gamma 1, and then I replace A by G gamma G dagger. So if you remember, this is the expression for the overall spectral function. Okay, now what I do, I basically subtract gamma 1 A1 from both sides. Okay, so let us simplify it further before we subtract. So now this part must be equal to trace of gamma G dagger gamma 1 G. Okay, so this is a cyclic property, so we bring this part to the left over here. Okay, and that is how we arrive at that matrix. And this basically is equal to trace of gamma A1, because this part of the matrix is basically A1. Okay, now we basically subtract gamma 1 A1 from both sides. So if we subtract gamma 1 A1 from this, we basically get, so let me write it here, trace of gamma 1 A minus gamma 1 A1 is equal to trace of gamma A1 minus gamma 1 A1. Now this A is equal to A1 plus A2, and this gamma is equal to gamma 1 plus gamma 2, so we can readily arrive at this expression, that trace of gamma 2 A1, sorry, this is gamma 1 A2, so trace of gamma 1 A2 is equal to trace of gamma 2 A1. Okay, so we have basically proved this thing over here. Okay, and this thing is equal to, so this thing, if I put the expression of A2 over here, what we basically get, we'll basically get trace of gamma 1 G is the Green's function of the channel, gamma 2 G dagger, which is equal to trace of gamma 2 G gamma 1 G dagger, and this is the function which we call the transmission function, which we denote as TE. So if we look at the expression in the previous page, there is no reason why this part should not be called the transmission function. Okay, because this basically decides how many electrons, or what is the quantity of the electrons that can pass through the channel. So F2 minus F1, this is like the driving force for the electron flow. Okay, and this basically decides if the electrons can flow through the channel or not. So let us say for the water to flow, you need to have a force that would drive the water, and you also need to have a pipe that can carry the water. So here this thing is known as the transmission function, and this is like the pipe. This serves as the pipe for the water, and this is like the driving force for the water to flow. Okay, so water is the analogous to electrons. Okay, so we can basically write this expression in a more compact way. So this I, this basically becomes equal to Q by h bar integral of dE divided by 2 pi dE F1E minus F2E. Then this 2 pi times h bar, this is equal to h, so Q by h integral of TE F1E minus F2E dE, and this is basically Landauer's formulation. So we will not move into more details here, because we don't have much time left, and I think the course has got a bit complicated towards the end. Okay, so this TE is basically our transmission function, and it is the probability that when an electron enters into from one contact, what is the probability that the electron can get out of the other contact. And this transmission function TE basically captures the entire configuration of the channel. Okay, and this is basically, again let me write it here, equal to trace of gamma 1 g gamma 2 g dagger equals to trace of gamma 2 g gamma 1 g dagger. Okay, now this is the ballistic formulation, that is, it assumes that when an electron enters the channel it doesn't suffer any scattering, so there is total coherence in the electron wave function. Okay, the coherence does not break. Okay, but in most realistic devices or in most realistic channel there would be phase breaking, so the coherence would gradually become poor as you move along the channel, as the electrons move along the channel, and those kind of things can also be introduced in the NEGF formulation, and this is generally introduced by or through this scattering matrices, which is known as the sigma matrices. Okay, we'll not go into the details of this here, but just know that we can do that, and that requires basically a modification of the Green's function through a modification of this scattering matrix sigma. Okay, so let us do up to here, and thank you everyone.